So the title of the workshop is Large-Scale Certified Numerical Methods. My interpretation of that when we came up with the title a few years ago was that the large scale was more on the computational side, and the certified part is more on the error analysis. And we heard from this morning that the first talk was mostly on fast algorithms, and the second one was more like correcting the basis set error. And so my talk would be combining a bit of both and about developing more efficient algorithms for hybrid functional calculations, which receives increasing amount of attention in the past decade, and also talk about the finite size effects, which is how do you approach the thermodynamic limit. I really think that this is the, I'm quite glad to talk about this topic here because our chair, Francois Gigi, is really a pioneer in this field. So for the exchange correlation functional, we know that there's this ladder. So the bottom three ladders are called local or semi-local functionals. There's hybrid and RPA, and beyond those are non-local functionals. So hybrid is somewhat like the sweet spot right now because RPA, those calculations, they're still kind of like a niche, and it's hard to do very large things. These things people really have pushed to very large scale calculations, and the increasing amount of attention in the past decade has been paid to do more and more hybrid functional calculations. They are also very useful ingredients for developing. What happened? Sorry. They are also very useful ingredients in terms of developing new machine learning functionals, for example, the recent DMINE's work. So just a recap of Kong-Sham DFT with LDA or GGA, it is mostly like a differential operator in the sense that you have a Laplacian operator plus local potential. There is a small non-localness in terms of the pseudo-potential approximations to the electron-ion interaction, but those don't depend on the density matrix. I think Francois will talk about that more in detail tomorrow. Then you solve many eigenvalues and eigenvectors. Here, the Hartree exchange correlation, it depends only on the electron density rho, and it's a diagonal potential. There have been many efficient numerical solvers developed for this problem. For example, Chen Feng 2 months ago gave a very nice tutorial talk on efficient numerical methods. It's a nonlinear eigenvalue problem associated with a differential operator. Differential because it's mostly Laplacian plus the diagonal potential. The meta-GGA is slightly different in the sense that it might modify this Laplacian a little bit, but the structure is pretty much the same, and the cost for solving this problem is similar. Kong-Sham DFT with hybrid functional, on the other hand, is a totally different beast. So it's more like a so-called integral differential operator. You still have this part, Laplacian electron nuclei, and the Hartree exchange correlation, but those parts are from the GGA or meta-GGA level. And here you have this non-local operator that not only depends on the electron density, but also depends on the density matrix. So what you're given here, it is given by like a kernel, Vxr prime, and so this one acting on psi I should be understood as doing an integral. And in practice, so there are two very popular choices that are very well cited in the literature, and one's called PB0, and the other one is called HSE. And the difference is that this is the bare coulomb, and this is the screen coulomb. To solve this with, for example, a plane wave basis set, you need to solve loss and loss of Poisson equations, and Chao mentioned that earlier this morning, and that is really a very significant challenge to large-scale calculations because you need to solve this so-called Hartree-Fock-like equations. You need to do self-consistent solutions of the orbitals, not of the density, but self-consistent solutions of the orbitals of the density matrix. And applying this exchange operator to the occupied orbitals take really, let's say, over 95% of the computational time when you do the large basis set calculation. So just a little bit more details on why the hybrid functional calculations are so expensive. This is the algorithmic, very high level algorithmic structure used by many codes, such as quantum espresso. And you want to solve this eigenvalue problem. There are two layers of iterations. The outer iteration, you do a self-consistent iteration on the density matrix, which is mostly like a fixed point iteration. You get a new P and you use it to construct a new Fock exchange operator, and you keep going on until it converges. And the inner iteration, you do a self-consistent iteration on the charge density to reduce some of the charge sloshing phenomena. And inside the iteration, this self-consistent on rho, you do an iterative method, your favorite eigenvalue solver or some other things, to solve a linear eigenvalue problem. And in this innermost thing, at every iteration, you need to apply this exchange operator to all the occupied orbitals, and that each of this set of applications requires solving NE square Poisson-like equations. And if some of you have done calculations in the plane wave basis set, you know that the solve the Poisson equation, usually it is only done at this level once you give electron density rho and you solve a Poisson, and that already takes some time. But if you do this at the innermost level and there are NE square of those to solve, you can imagine how much time it costs. That's why it is super expensive. So this structure actually presents three kind of like a separate problems, although they're sort of correlated with each other, but more or less separate. One is that the V in terms of Vx, the exchange part, in terms of the magnitude is relatively small. It's about 2%, 5%-ish of the in terms of the operator norm, but it is applied very, very frequently. As you've seen, it is embedded at the innermost level of the calculation. Not every code is like that, but many codes are like that. And applying this thing once is already pretty expensive. And also, this increases the number of SAF iterations because you not only converge with respect to rho, but also converge with respect to the density matrix P. There, of course, the community is very well aware of these issues, and previously there have been many, many works trying to address these problems from various aspects. Some of the experts in the audience have contributed to this field. Here I'm only focusing on the large basis set calculations rather than the small basis set, such as in quantum chemistry when you use Gaussian type orbitals. The problem there is very, very different. I can go into length, what the differences are, but to make the discussion simpler, let's just think like large basis set in the sense that you don't even want to form the Hamiltonian or the Fock matrix. You can only do it iteratively. So in order to apply this thing faster, you can go to massive, massive parallelization because this NE square Poisson equations can be trivially parallelized once those data are on the right processors. So you can use really a lot of CPU cores to do this. Nowadays, you use GPUs. You can use localization to make this effectively a sparse matrix. Those things work very well for large band-gapped systems such as water. They work less well than the for small band-gapped systems or metals. You can do density fitting, and we heard Chao talked about that earlier this morning. You can apply this Vx, try to apply it less frequently. For example, Francois has a number of works on this before. It's this paper, I think. And also you can reduce the number of the cost of SAF. You can use optimization-based strategy instead of using self-consistent field iteration. But they're not so widely used yet. So our approaches in the past couple of years is a little bit different. Today, I'm only mostly going to focus on this adaptively compressed exchange. It has, we analyzed it later with the Michael Lindsay, and also inspired some other optimization-based algorithms called the structured Quasi-Newton method. And you can think it's a so-called a Nystrom type of method in the optimization literature. This one is mostly to reduce the frequency for you to apply the exchange operator. You can do that without making any error, actually. So it's a sort of like a free lunch. So the second one is not totally a free lunch because you do make a lossy compression. And this is the interpretive separable density fitting that was pioneered by Jianfeng Lu and Lexing Ying. And later we did some work together with Chao and Wei developed along this direction. Recently, Wei's group has done some very nice works of combining this ACE and ISDF for the K-point calculation for solids. Chao gave a detailed talk on this earlier this morning. You can also try to improve the self-consistent field iterations, to mix a projected version of the density matrix. We call it a projected commutator DIIS. This CDIIS is, to our knowledge, one of the most widely used strategies in quantum chemistry literature. It's hard to directly use it for large basis set calculations, but we made some improvements on that so that you can do it within the plane wave basis set. This is what we did a couple of years ago to test the accuracy and together with Amartya, who's also in the audience. You go from silicon systems, go from unicell to much larger system size, and you first test the accuracy of the ACE. The inner solver is using this locally optimal blocked preconditioned conjugate gradient, and compare that with the conventional HSE solver, and you can see that pretty much everything agrees with each other very well, and the remaining discrepancies are just we terminated the SF iterations. If you let it go on, it will converge to all digits. So then you can combine these techniques together, and that has been really some progress in terms of the speed that has been made in the past few years. At least within our own code called DFT, we implemented this thing, and everything's tested within the same code base. Our Poisson solver should be may not be the best, but it should be reasonably optimized. If you do the hybrid calculations of this silicon with 1,000 atoms, so the cost, the conventional solver, which is the pseudocode I showed you earlier, takes about 12,000 seconds. This is what I mean is the calculation from the beginning all the way to the end. So this is the total time to converge it, not like just a single SF step. So that's like on top of the roof. Just by using ACE alone reduces the cost by a factor of 8 or so. And so this strategy has been integrated into a number of community software packages such as Arbinate, PWDFT, Quantum ATK, Quantum Espresso, WASP, so on and so forth. And so there have been a few papers on this. For example, one of our speakers, Stefano Baroni, and his group did some work on this in QE, and that was 2018. Recently, I think Xavier Gonz's group and has a paper, Arbinate, and I think this is the recent development paper, and the ACE is now the default solver in Arbinate for doing hybrid functional calculations as well. I think that's also the default solver in quantum espresso. So this one is widely used because it's pretty much like free lunch, as I said. Then if you adopt like some further lossy compression, you can slash this by a further factor of almost 3. If you combine this with the PCDIS to like reduce the number of iterations, you further slash it by a factor of 3 or so. Combining everything together, so in the past few years for this particular system, you can achieve more than 40 times speed. What it means is pretty much the time is close to the GGA cost. Remember, as I said, it used to cost like 95% of the time, right? 95% sounds like a lot, but if you really think about that, that's like 20 times. So if you can really slash this factor 20, you're pretty much there. And so this is from the algorithmic side. Because of time, I want to talk about the second part as well. So I'll just explain the idea behind this adaptive compression. So the ideas are the following. So usually when we think about the low rank approximation, we think about in terms of SVD, the singular value decomposition, and its variance. The idea of SVD for a matrix, if you look at that from a vector perspective, is to say that, okay, you give me a matrix called Vx. I want to find a surrogate called Vx tilde so that their difference is small when applied to any vector or any orbital, right? And the famous Eckart-Young theorem says that the SVD is optimal in terms of optimizing the residual. So, but this is not what we needed. First of all, this is not achievable because the exchange operator is a full rank operator. If you just truncate it to some like low rank, it just doesn't work. So, but this is not what you need either, because even though the singular values of Vx decays very slowly, what we really want in this hybrid functional calculations is that I want to find a surrogate so that the difference between Vx and Vx tilde is small when applied to any occupied orbital. Furthermore, I want this thing to be not only small, but actually zero. Okay, so the difficulty, of course, is a chicken and egg problem. I don't know the converged occupied orbitals to start with. So I have to do this iteratively. I have to make a guess. What are the occupied orbitals? I make a compression. I get a new guess, and so on and so forth. Hopefully, this thing magically converges. So that's the basic idea. Sounds like a tall order. So as I said, the uncompressed exchange operator is not only a full matrix, it's also a full rank matrix. But you want to adaptively compress this exchange operator and so that the rank becomes much lower and you will maintain the accuracy. So this is the hope. The procedure is actually not that complicated. So you still apply this exchange operator to all the NE. NE is the number of electrons, like NE orbitals. Okay, so this is what you do in every code, and to get this vectors called Wi. Then I want to construct a surrogate called Vx tilde or Vx ACE. It needs to satisfy two things. Here I'm using real arithmetic operations for simplicity. So Vx applied to the trial occupied orbital phi needs to be the same as applying this true exchange operator. So this step, each evaluation is pretty expensive. You really solve Poisson equations to do it. And also needs to be Hermitian because we're solving a Hermitian eigenvalue problem. So there are many different forms that would satisfy this. The simplest choice is to let the column space of this Vx ACE to be the column space of W. Because of a Hermitian condition, the row space should be the same. This pretty much says the kernel for this adaptively compressed exchange should be Wi transpose, and in the middle you have a coefficient matrix to be figured out. So how to figure out this coefficient matrix? You can do a projection step. You can project this thing to the occupied orbitals, and this gives you a linear algebra problem. So on the left is a matrix called M, which is an overlap type of matrix. You will see that you end up with the equation of the form overlap equals to overlap unknown overlap, and this overlap can be evaluated directly, and then this gives you B. So you're done. Okay, so that's the entire procedure. Well, why it works is a totally different story, but the procedure is like that. So you can even make it look like a pseudopotential in the sense that this M is known to be a negative definite matrix. So you can do a Cholesky factorization for the negative M. You can do some other factorizations. So you do a linear combination of this Fock potentials. So this Vx-ACE is a strictly rank NE operator that looks just like a non-local pseudo-potential in a Kleinman-Barlander form. So that's the procedure. Does it make sense? Any question? Okay, so how are you going to use this? So the idea is that you apply the outer iteration, you do a self-consistent iteration on this occupied orbitals. You apply Fock exchange operator to these orbitals. You follow the recipe to get this Vx-ACE. And the innermost iteration, whenever this Vx is used, it replaces it by the surrogate. This one, the application is just a two-matrix multiplication. It's extremely cheap. And you only do this expensive step outside. There's no loss of accuracy, and assuming the converges to the same fixed point. And there's no band gap assumption either. And we have tested a lot for both insulating semiconductors and metals. How does it work? So to understand how this method works, we look at the simpler problems, which is like linear eigenvalue problem. So it takes the form A plus B eigenvalue. You want to the lowest n eigenvectors, where A, B are Hermitian matrices and of size capital N by capital N. Capital N is much larger than the number of eigenvectors you want. So capital N is like the number of plane waves you have. Small n is the number of electrons you have, and you have a lot of electrons. So that's the regime, parameter regime we're interested in. B is a negative definite operator because exchange is negative definite. It is super important. Otherwise, you will, if you do some sort of compression, you get all sorts of intruder states. Yeah, so this negative definiteness helps a lot. We also assume that this A part has a spectral norm that is much, much larger than the spectral norm of B. This is also reasonable because A is Laplacian, is a differential operator, is unbounded, and B is an integral operator and is bounded. So, and we use a lot of plane waves, so which means that the A part, the differential operator part, has a pretty big spectral norm. So we also, for technical reasons, assume that there is a gap to facilitate the analysis. So the adaptive compression is a pretty weird scheme if you think in this particular context, because there's no nonlinear. This is a linear eigenvalue problem. The problem we really want to solve is a nonlinear one, as you saw before, but that's nonlinear ones are hard to analyze. But in the context of linear eigenvalue problem, the adaptive compression method sort of like splits a single loop of iteration into two loops. So what we assume is that, another assumption is that A applied to a vector is cheap, but B applied to a vector is very costly. That's because A is a differential operator, B is the integral operator. So if B applied to a set of vectors is very expensive, what we want to do is every time we do this set of matrix vector multiplications, we want to reuse the information as much as possible. So, which means we want to create a surrogate. So the idea is the following. You give me any set of n, small n vectors V, and I define this B bar applied to V, is using this BV together with this coefficient inverse matrix, as you saw before, times the transpose of like a BV star. So this is a low rank matrix. The rank is a small n. It obviously satisfies a consistency condition. That's why in the end it could be a lossless compression, which means B underscore V applied to V is V star BV cancels with this inverse is BV. So if V is exactly the guy you want, then B, it doesn't matter whether you apply this B or apply this low rank guy. Right? So now what I want to do is to construct the following iterative procedure. You convert a linear eigenvalue problem to a nonlinear eigenvalue problem because you iterate on this V. So at the kth outer iteration,
you solve this modified linear eigenvalue problem, which is A plus a low-rank matrix, and figure out the eigenvalues and eigenvectors. Yeah.
Initialization. You start from
initialization. For example, you just think B is 0. Yeah. Any other question? So you see, this is indeed a nonlinear eigenvalue problem, and yeah. So yeah. Okay. So I didn't say that. So so you see, these indices are different. So what you can think here is that when going from k to k plus 1 iteration, you're just doing a fixed point iteration. You can, of course, accelerate that with DIS or some other things, but fixed point iteration turns out to be good enough for analysis. So miraculously, this thing converges, and is actually provably converges. But when we talk about the convergence of the thing, we need to talk about some sense, which is in terms of the orthogonal projector or the density matrix. Then what you can show is that not only converges, but also with a rate. So if you give me any Hermitian matrices A and B is a negative definite, then the adaptive compression method stated earlier converges locally, means that you start from a local neighborhood of the true density matrix. It converges locally to P. And the number of iterations needed with k iterations is n, right? So this expensive matrix vector multiplication is n times k. N is the cost like per iteration. And you also have the asymptotic convergence rate, which is gamma to the k. And importantly, this convergence rate only depends on parameters related to the gap and also the spectral norm of B. It has nothing to do with the spectral norm of A, which is the large guy. So this is really how you save the cost. Another very interesting observation, and the mechanism is completely different, is that you can even prove global convergence. So the global convergence, the statement is weaker, and there's no way you can talk about convergence rate, but you can have the following result, which is you take almost all Hermitian matrices A and B, taken randomly from according to the Lebesgue measure, and also require B to be negative definite. And then starting from almost all initial guesses P0, then this method converges globally to P. It sounds like a miracle, but the phenomena is similar to in the machine learning literature, that people say that steepest descent method can converge globally to somewhere. And the idea is that most of the other things, they are not local. They're not local minima. They're just saddle points. Therefore, you just perturb a little bit, and you will go away from the saddle and all the way to the local neighborhood. Okay. So then let me talk about finite size effects. So we have learned from one of our main organizers, Alexander Tkachenko, and there have been like many discussions throughout this long program about the physical interactions and power law decays. Most physical interactions, they interact with the power law. So Coulomb interaction goes like 1 over r, dipole-dipole goes like 1 over r cubed. If you think about van der Waals and with this induced dipoles, permanent dipoles, so on and so forth, you get this r to the minus 6. And these long-range interactions, it creates a lot of problems when you go beyond the molecules and want to study the solid-state systems. And these are so-called finite size effects, or the error when you approach the thermodynamic limit. You can do hybrid functional calculations for solids, but then you have two perspectives. And there are two perspectives for dealing with the solid-state systems in general. One is real space. You really take advantage that there's some translational invariance when you move from one side lattice to one unit cell to another. Or you can view that in the reciprocal space. You restrict to one unit cell and have a lot of so-called k-points. And then you discretize the reciprocal space the first Brillouin zone using the so-called Monkhorst pack grid, which is basically a uniform grid or called a trapezoidal rule. And with some momentum conservation, Ki plus Kj equals to K plus Kb, you get rid of one of them, and that reduces the computational cost as well. So we're going to focus on this perspective because that converts a lot of the problems into a quadrature problem. These finite size effects can be very, very significant. This is for the computation of the Fock exchange energy from a paper by Carrier, Bora, and Gording, PRB in 2007. And if you look at the exact exchange energy without any correction, and this looks like this, it doesn't look too bad, but if you look at the scale, this is like, 50 eV, right? And it's enormous. And with some corrections, things become better, but it's still very far away from chemical accuracy-ish. So if you don't do finite size effects, and this is a disaster. And later we're going to see why this is a disaster. Correcting finite size errors for solids in general, and so there have been many important works in this direction for the Fock exchange, and Francois did that like in the 80s, and that's still one of the most widely used correction schemes for the Fock exchange, and there has been a lot of improvements like since then. And to our knowledge, we're pretty new to this field. The finite size effect has been most systematically studied. Beyond the Hartree-Fock level, has been most systematically studied in the quantum Monte Carlo community. And David in the audience is an expert, one of the leading experts in this area. And one of our favorite papers in this is earlier by Fraser, Folks, and collaborators in 1996. Really has a lot of useful information, and this has been developed by many people afterwards. And recently, there has been increasing interest in studying the finite size effects for post-Hartree-Fock quantum chemistry methods, such as MP2 or couple cluster, and so on and so forth. Greenis and other people have done a lot of work in the past few years. So our current understanding is that there are, if you really look at the finite size effect by treating that as a quadrature problem, the issue has not been resolved even at the Hartree-Fock level, not to mention the post-Hartree-Fock level. And so this is something I want to present. So let's consider the setup. The setup is that you have a unit cell omega, and the corresponding Brillouin zone is called omega star, and the Bravais lattice is called L, and the reciprocal lattice is called L star. So the Coulomb interaction, which is the source of all problems, so is 1 over r in the reciprocal space, looks like 4 pi q plus g squared. So for those of you not familiar with the literature, q, this is just a single index, but you separated them into two. Q is in the first Brillouin zone, is in this compact thing. And G is in the reciprocal lattice vectors. And it's usually the convergence with respect to G is usually called the complete basis set error. And we have heard from the previous talk and on the basis set error. We mainly focus on the convergence with respect to Q. Yes.
I'm surprised you say that finite size effects are mostly due to the Coulomb, because the dominant ones are coming from kinetic energy, as long as you have a small gap.
Oh, okay. I should revise the sentence, which is for the problem I'm going to talk about in this talk, especially the Fock exchange energy and the MP2 and the RPA correlation energy. Those are due to the Coulomb. Yeah, because
it has to do with, a Fermi surface or a near Fermi surface causes big effects.
Okay, yeah. Maybe I'll continue and see whether those things are self-consistent. And okay, so this one has a like long-range behavior. So the long-range behavior in R can be translated into the short-range behavior in Q, and most finite. Maybe this is I should revise this one. So, for example, if you look at how bad the situation is, if you just look at a group of periodic point charges with a not like net zero charge, this rho r, and in the Fourier space called the rho g, if the rho hat at g is not equals 0 is not 0, this is like a net charge, then this thing directly diverges. So the Hartree potential diverges, and you definitely need to do something. More subtle effects, such as the Fock exchange energy, takes the following form, which is more this F is not like a bunch of Dirac cone. You need to integrate with respect to Q, and this is an integrable singularity, but that will still create a lot of troubles when you try to converge it. Why this is an important issue? And as you have seen that from the previous picture, that the exchange energy, if you directly converge it, that's like right, the number of K points is already 500, which means that there's 500 unit cells, and still the error is pretty large. If you really just converge it by brute force, even with a very good large-scale solver, that's not the way to go. Further, some setup. So we consider the Hartree-Fock band. So to address David's question earlier, we assume that the Hartree-Fock bands or the wave functions are obtained exactly. Which means that the corresponding error to the kinetic energy is negligible. Of course, that's an assumption, but even under this assumption, the finite size scaling is still pretty cause a lot of headache. So this is the non-periodic version of the Hartree-Fock band. You can separate it out into the phase and also a periodic part, and that can be expanded in terms of a Fourier expansion. So this 1 over square root of nk is the number of K points, or equivalently, the number of unit cells in the supercell is you have this scaling, it's a natural scaling, so that this is L2 normalized within the unit cell, this is L2 normalized within the supercell. So you define a so-called pair product, which is a real space Hadamard product, as you have seen earlier in Charles' talk. And then you can define the two electron repulsion integral called ERI using this Fourier coefficients, and takes this form. And this one is due to the crystal momentum conservation. Then the Fock exchange energy can be written simply using the ERI tensor as the following. So you sum over all the Ki, Kj within the Monk-Horst-Pack grid and sum over all the occupied states. You reorder this a little bit, you can write it to be a sum over this Fxij coming from the contribution for the exchange. And when we say it approaches the thermodynamic limit, it means that we replace the sum by an integral, and we want to consider the difference between the two. So mathematically, this is nothing but a quadrature error analysis, because Monk-Horst-Pack grid is nothing but like trapezoidal rule. So you give me a uniform mesh defined on some called X, defined on some domain, and the trapezoidal rule to integrate the function g is just this. The quadrature error is the difference between the value you get from the integral and the thing you get from the quadrature, which is given by this. And in particular, the Monk-Horst-Pack mesh is exactly of this form. So our main result, which includes both the exchange and Madelon corrected exchange, as well as the MP2, is the following. And so Shane, I believe, will talk in more detail later this afternoon. I'll just talk about the basic idea. And first of all, there is a provable nk to the minus 1/3 convergence rate, which is really, really bad because you just increase your system size, let's say, along each direction by a factor of 2, which means the total number of atoms increased by a factor of 8. and the computational cost is 8 to the cube or even more, and you only reduce the error by a factor of 2. So this is really challenging. That is why in practically all Fock exchange calculations, there is some sort of correction going on, and such as the so-called Madelung constant correction is the most basic form. You can also do it better using the so-called singularity subtraction formalism. This will improve it provably to nk to the minus 1, and with some new methods called the staggered mesh methods, you can further improve it beyond nk to the minus 1. And another thing is we can analyze MP2 calculations and get a similar convergence rate, which I won't talk about it here. For lower dimensional systems, such as, let's say, graphing or maybe a gapped version of that, boron nitride, things become more complicated. In particular, it depends on how you define how you set up the low-dimensional system. We have a particular version for setting up the low-dimensional system, which still assumes periodic boundary conditions along all directions, but the k-point refinement is only along a particular direction. In this particular model, what you can prove is that for quasi-2D things, with the Madelung exchange, you can get to this rate, but with the staggered mesh method, you can improve it further. And for 1D, you can even, with some algorithmic improvements, you can even get to the so-called super algebraic convergence, which is when you do it for nanotube-like things. And that is due to some sort of a removable singularity. So let me, maybe in the next few minutes, briefly say what are the challenges, why I was claiming earlier that the convergence rate, even for the Fock exchange, is still was not rigorously established till this work. So the reasons following. So if you look at the integrand called fx, is a periodic with respect to ki and kj. So, but there's some singularity at the kj minus ki called the momentum transfer. So you can do a change of variable to be ki and ki plus momentum transfer. You integrate out the nice guy, then the quadrature error is dominated by something like this, integration with respect to q. So the behavior around q equals 0 is the following. Without the Madelung correction, this f0 is approaching 1, so that doesn't look good because this thing looks like it is blowing up. And with the Madelung correction, what you have is a quadratic over quadratic form, which is still bad. Because a quadratic over quadratic means that when q equals 0, this thing has a well-defined limit, but its derivatives are just unbounded. So that's still very bad from the perspective of quadrature error analysis. The standard way for analyzing this kind of thing is called the Euler-Maclaurin formula for the quadrature error of the trapezoidal rule. The starting point is the integrand needs to be at least C1. And then you start to talk about business. But the problem is fq over q squared, even after correction, is not C1. So the Euler-Maclaurin analysis gives you overly pessimistic result. Note that I'm not saying the scheme doesn't converge. The scheme still converges, but the error analysis is very bad. In fact, if you just carry out the textbook analysis, it tells you that there's no convergence rate for either Hartree-Fock or MP2 in any setting. It is really bad. So the question is, for this type of integrands with a lot of singularities of a particular form, and you still want to use a trapezoidal rule, which is designed for smooth functions, what kind of convergence rate you can get from such analysis. So as I said, the technical challenge is really to analyze the quadrature error of a multidimensional. For one-dimensional, there are a lot of documents, but for multidimensional analysis, there are not that much work. This trapezoidal rules with a certain type of singularities. The particular singularity we consider is the so-called fractional form. This form turns out to be enough to analyze the error of the Fock exchange operator, Madelung corrected Fock exchange MP2, RPA, up to any finite order, but not beyond. For example, MP3 doesn't fall into this structure, and we couldn't analyze it yet. But yeah.
Can you just convert a multidimensional integral to a one-dimensional integral by integrating over the angle?
Yeah, well, but the integrating over the angle, that part doesn't is not consistent with the Monkhorst-Pack grid, right? So you really assumption is we literally take the scheme coming out of the code and we analyze that. Good question. Okay, so the fractional form is that you take this n is an arbitrary thing, depends on the level of theory, roughly like you can think like NPN, and each xi is a d-dimensional thing, and you have f1 over quadratic to the p1th power, f2 over quadratic over p2th power, fn over quadratic over pnth power. It seems really complicated, and each of them can be singular to some negative power. But the total amount of singularity needs to be controlled so that this thing is still integrable. So here's the technical improvement that allows us to do the analysis said above, which is for this particular type of integrand with the singularity described before on the rectangular domain on a cube, like with a uniform mesh. And you can also apply relative shift. That doesn't matter. The quadrature error takes the following form. There's the complicated stuff, and then there's the remainder. But the important thing is that if G, this integrand, and all its derivatives are actually periodic, which is the case for the Fock exchange, you integrate over Ki and Kj, and these derivatives on the boundaries will be integrated out to be 0. And then the leading error is up to the logarithmic factor d plus a gamma mean, and the gamma mean is the negative power that you get from this singularity. So what does it mean? So what it means is that let's look at a few examples, and so this is corresponds to the case n equals to 1. We study all sorts of combinations to test the sharpness of this result, and the theoretically predicted scaling should be m to the minus 2, m to the minus 1, m to the minus 5, depends on how you do it. And and also you can do the multidimensional thing. This starts to get pretty expensive because this is really you need to carry out a multidimensional integral. In all the cases, the convergence rate is sharp. Now, we don't know about the logarithmic factor, whether it's sharp, but other than that, it's sharp. And from this and the previously mentioned convergence rate for the Fock exchange and the MP2 becomes a corollary. Let me just briefly say maybe an interesting idea for the Fock exchange motivated by this analysis. I'm not aware of this scheme used in any practical code, but nonetheless, it's interesting to think about. From the analysis, it suggests that if you do the following weird way for computing the Fock exchange, the convergence rate is faster. What is the weird way? So you need to integrate over the Ki and the Kj, right? But if you let Ki be on one Monkhorst-Pack grid, let Kj be on another Monkhorst-Pack grid, that's literally shifted a little bit. But what does that do? That makes the Q, this momentum transfer, to be non-zero. And if you shift it exactly by half, which is here, and then so the KQ grid will be away from 0, and you can show theoretically the convergence rate should be faster. This is exactly what you observe. For 3D systems with the staggered mesh, it converges like nk to the minus 5/3, which is better than nk to the minus 1. For 1D, you get a super algebraic convergence. Whether this is a useful scheme in practice, we don't know, but at least it shows the analysis works. So, okay, let me just conclude with the following picture of our current understanding of the finite size effects. So, Fock exchange, there have been a lot of work studied, both from the correction schemes but our analysis, to our knowledge, is still new. Wasn't established in the literature because of the difficulty of analyzing this singular integrand. We know how to do MP2, at least for the insulating case. For RPA, we're somewhere there, which is we have a paper, but that only works for insulating systems up to any finite order of diagrams. How to analyze that for the renormalized one or for metals, we have no idea. We're making towards the GW and MP3, we think that there should be a lot of hope to expect that similar results can be worked out, although the technical details will be different because the form of the integrands are very, very different. Couple cluster is somewhere that we have absolutely no idea how to tackle, and QMC is probably there. And so I'd like to thank collaborators, Wei Hu and Michael Lindsay, Ron. Xiaoxu Li was a visiting student during the pandemic, from Beijing Normal University. She's here, and also a lot of work has been done with Chao in the past many years. And thank you.